And using theta, theta is the angle between the horizontal and wherever your latitude is, whatever angle that is, whether it's 0, 20, 45, 60, okay, that's theta. Now, those three quantities, r, capital R, and theta, they form a right angle triangle. So I can use SOHCAHTOA to actually figure out an expression for r, and that's down here. Small r is equal to the hypotenuse, capital R, times cosine of theta. So this will come in handy. All right, so at the equator, r, the distance from your rotation axis, is equal to the radius of the Earth, right? When you're at the North Pole, the distance from the rotation axis is 0 because you're on the rotation axis. Okay, so if you're at the equator, r is equal to that 6.4 times 10 to the 6 meters, or 6,400,000 meters, right? So we can figure out the centripetal acceleration at the equator. Okay, so if you're asking yourself, why are we finding centripetal acceleration? Well, for the reason that I just explained in an elevator. If you are in an elevator that is accelerating, and we have acceleration here, right? Centripetal acceleration, your normal force will not equal to weight, Fg, your force of gravity. It's going to be a little bit off. So you have to use F net equals to ma to figure out, well, how do normal force and weight balance? And they balance with mass and acceleration. So we're going to find out what the accelerations are. So again, at the equator, the acceleration is r times omega squared. We saw this formula before. The radius at the equator is the radius of the Earth, 6,400,000 meters. Omega is right here. We found it already, okay? So that number is getting squared. When you multiply the two, we get 0.0338 meters per second squared. Okay, at the pole, we said that r is 0, the distance from this rotation axis to where you are. There's 0 distance. Okay, if r is 0, it doesn't matter what you multiply it by, your centripetal acceleration is 0. Okay, so now, all right, so we've got two different accelerations. Let's figure out net force. Now, when you're, let me use this as an example. When you're on a certain position on the Earth, okay, so let's say you're on the equator, wherever you are, the gravitational force always points toward the center of the Earth when you're on the Earth. We usually say down, but down is toward the center of the Earth. So at this position, the weight is going towards the center of that circle. Normal force is perpendicular to the surface, so my normal force is going out. Now, that's true for any point that you pick. If I pick someone down here in the southern hemisphere, my weight is still going towards the center of the circle, and my normal force is still perpendicular to the surface. They're still in opposite directions. That's fine. It doesn't matter where you draw it. Now, usually when you have acceleration, the best strategy is to pick your positive direction as the direction of acceleration. So I have this scenario where the centripetal acceleration is toward the center of the circle. So that means I'm going to let toward the center of the circle be my positive direction. Okay, so usually when we have linear problems, we would say left. Okay, left is positive and right is negative, and where up is positive and therefore down is negative. With circular motion problems, it's either that towards the center of the circle is positive and radially outward is negative, or the opposite. Radially outward is positive and radially inward is negative. Generally, it's better to pick radially inward as positive, well, because that's the direction of centripetal acceleration. It always will be. So, anyway, so inside toward the center of the circle, that's positive. That means a weight will have a positive sign and normal will have a negative sign. Okay, so when we look at Newton's second law, the sum of the forces is equal to m times a. That means weight, which is in the positive direction, minus normal force, since it's in the negative direction, equals ma centripetal. All right? We're trying to find apparent weight. That's the normal force. So rearranging this expression for normal force, minus n goes to the right, positive mac comes to the left, and you get this next expression. N is equal to w minus mac. Now, weight. I was already told that the person's weight is 882 newtons. That's it. But I know that that weight can fluctuate depending on where you are. And since I'm at the equator, I have to subtract NAC. Now, how do you find the mass? Okay, so if you're wondering where this next line is coming from, we're using this formula. W is equal to mg. So how do you find m? M is just W divided by g. Well, what's the weight here? It's 882 newtons, right? So 882 divided by 9.8, that's m. Okay, so if you're wondering what's this in the bracket, that's m. M is this. Multiply that by AC, we just found that on the previous slide, 0.0338, and you get 879 newtons. Now, if you remember with a point on the top, at one of the poles, we said that there was no centripetal acceleration because your R value was 0. So if AC is 0 for a point on the poles, that means N is equal to W, which is what we had, right? Your weight would have been 882 newtons. But it seems like the further you get away from the poles, your scale will read something a little different. And in fact, we find that at the equator, the scale would read 879 newtons. That's 3 newtons different. Okay, so it just goes to show that, well, depending where you are, you're going to have a different normal force acting on you. Okay, let's move into some sample problems now. We've been doing a lot of examples. Oh, and there's the normal force and the weight. However, I already drew it over there. We're going to move into some problems. Even though we've already done a lot, such as this one, you'll get a taste for actual homework style problems or test style problems on the next slide. Okay, the next few slides, I should say. All right, here we go. Let me erase the board first. A linear spring of negligible mass requires a force of 18.0 newtons to cause its length to increase by 1 centimeter. Just pause for a second. That kind of information is trying to help you find some kind of a quantity which you can use later in the problem. Okay, I know that the spring requires that force to increase its length by that much. Guess what I'm going to be able to find? I'm going to be able to find the spring constant. So just keep that in the back of your head. A sphere of mass 75.0 grams is attached to one end of the spring. So there it is on the right. The distance between the center of the sphere M and the other end P of the unstretched spring is 25 centimeters as shown below. So most likely this thing is getting whirled in a circle, just as if you were to have a ball attached to a string. It's whirled in a circle. Except now instead of a string, you have a spring. The sphere is rotated at constant speed, so we have centripetal applications here. In a horizontal circle with center P, the distance Pn increases to 26.5 centimeters. So it started at 25, now it's at 26.5. So the first question is, well, why does it increase in length? Okay, so it might make intuitive sense why it does. I mean, you've got a spring and you're waving the spring in a circle, the spring's going to get longer, right? But why is that? Okay, so you know why, but why is it? When you're waving it in a circle, when you're spinning it, all of a sudden the speed goes from 0 to something that is non-zero. And the fact that it's moving in a circular path, that's centripetal force. So Fc is equal to, well, whatever you have there, that's the spring. So Fs. You can set Fc equal to whatever force it is. Friction, normal, tension, gravity, magnetic, electric. You always can set that equal to something if it's applicable in that case, which it is here. So mv squared over r. Now in the data booklet, they use kx instead of ks. I personally prefer ks, but I'll just use x so it's consistent. All right, so the mass is not changing, right? The mass on the end of the spring is not changing. This is constant. The radius of the circular motion, yeah, that's changing. We're trying to figure out why r is getting bigger. R, in this case, I mean, that's similar to x. X is the amount by which the spring stretches. So if x gets bigger, that means r gets bigger. So they're kind of one and the same thing here. Okay, so what we notice is that when v goes up, x has to go up. And really, that's all you have to explain. Okay, so you intuitively understand why what's happening is happening, but there's the explanation that goes along with it, okay? The reason it's spinning in a circle, the spring force is equal to the centripetal force, and we can clearly see from this, if the speed increases, X will increase. So that means if you spin it even faster, it will get even longer. And I'm sure that makes intuitive sense to you as well. All right, part B, determine the speed of the sphere. Well, I mean, I've already got this set up, so let's figure out how to determine the speed. So this is part B now. So if I rearrange for speed, it's going to be kx times r divided by mass square root. All right, so x, I know that's the amount by which the spring stretched. It went from 25 centimeters to 26.5 centimeters. So that's 1.5 centimeters or 0.015 meters. So there's x. My r value, that's the distance from the axis of rotation, my r value is going to be 26.5 centimeters or 0.265 meters. Let's see, what else do we have here? The mass at the end of the spring, 75 grams. So if we divide that by 1,000, we'll have 0.075 kilograms. And what else? We've got X, R, M, we need K. So remember at the beginning I said K is going to come up? Well, there it is. They don't tell you K directly, but they tell you how to find it. That first line there. K is the spring constant. It tells you how much force is required to stretch a spring by 1 meter. Okay, so tougher springs will have bigger spring constants. Every spring, for our purposes, has the same spring constant no matter how much you stretch it. Okay, so we have a force which is equal to K times X, the force being 18 newtons, and the corresponding stretch being 1 centimeter. So 0.01. So that means K, I mean, effectively that's 10 to the minus 2. So if we divide that, 18 divided by 10 to the minus 2, that's 18 times 10 to the 2, sorry. 1 times 10 to the 2, so that would be 100. So multiplying 18 by 100, that's 1,800 newtons per meter. Okay. So we have our spring constant. Let's plug in our values. So 1,800 times x, 0.015 times r, 0.265 divided by 0.075. So we just have to plug in our numbers, and that's it. All right, here we go. Let's just use the calculator here. All right. 1,800 times 0.015 times 0.265 divided by 0.075 square root, and we're getting approximately 9.76 or 9.77. Now, in our question, the least precise numbers, or the number with the least sig figs is the 1.0 centimeters, so we're going to have that. So 9.8, it's a speed, so meters per second. Don't accidentally write per second squared because it's just 9.8. Okay. Next problem. So I'll leave actually that up, but same solution is up on the board. If you want to take a look, pause the video and inspect it in more detail. All right, next. Points P and Q are at distances r and 2r, respectively, from the center x of a disk as shown. The disk is rotating about an axis x, normal to the plane of the disk. Okay. Point P has a linear speed v and centripetal acceleration a. Which one of the following is correct for point Q? Okay. So on the top here, you're going to notice two formulas come up. Use v is equal to rw and a is equal, r omega, and a is equal to r omega squared. So, I mean, we notice something right away. For point P, okay, speed is equal to r times omega. Well, they have the same omega, right? They're covering the same angle in the same time, but their radii are different. So for point P, your V is going to be equal to capital R times omega. Let me actually write this down so you see what I'm talking about. Okay. So for this, so we're going to use V is equal to R omega, and we're also going to use the other formula, A is equal to R omega squared. So for point P and point Q, we're going to make some comparisons. So point P, we're at radius R. At point Q, we have radius 2R. Do we know any other information? No, not yet. Okay, so that means let's start with speed. It's on the left, most likely that one's coming first. So speed is equal to R times omega. And I just mentioned that the omega values are the same. They're covering the same angle at the same time. So this one has omega, this one has omega. So the speed for P is equal to capital R times omega. Okay, let's look at the speed for Q. Speed is equal to little r times omega. Well, the omegas are the same, but the r is double. So we have 2r, right, that's r times omega. Now, r times omega is velocity of P. And this here we're solving for Q. So therefore, velocity of Q is 2 times velocity of P. This is Q right here. And this is P. Well, that's the general formula, but this is now P. So I can see that the speed is becoming double. That means the answer is either C or D. It cannot be A or B. Okay, actually I'll do it here as well. Let's do acceleration now. Acceleration is r omega squared. Now in this case for point P, my r is capital R, the omega is just omega. So the acceleration for P is r times omega squared. Let's do the same thing for Q. So acceleration is equal to r omega squared. So the acceleration at Q, now r is 2r. It's the same factor. 2r, omega is the same, while r times omega squared is acceleration of P. So now I have acceleration of Q is 2 times the acceleration of P. So that means it's also doubling, which means the answer is C. And all of that is on the slides as well. The last piece here, the last slide, and the last question is this one right here. A brick is placed on the surface of a flat horizontal disc as shown in the diagram. The disc is rotating at constant speed about a vertical axis through its center. The brick does not move relative to the disc. Which of the diagrams below correctly represents the horizontal force or forces acting on the brick? Believe it or not, this is a very common question where students make a mistake. Imagine this was a car taking a turn on a flat curve. It's a horizontal disc. Imagine it's a horizontal curve. The car is taking a turn. The reason the car can take the turn is because of static friction. Which way does the static friction point? Towards the center of the circle. If you have the ball attached to a string, if you whirl this in a circle, the force that is allowing it to turn in the circle is tension, and that tension is pointing towards the center of the circle. Centripetal force, the force responsible for objects moving in a circular path, always points towards the center of the circle, as does the acceleration. Okay, so, well, what's keeping the brick on the disc? Okay, it's not super glued there, it's just put on top. It's friction, static friction. Okay, that's the only force acting on it. And the static friction has to point to the center of the circle. This would be incorrect. If the force was going left, it would fall off. This is not correct. Now, a lot of students mistakenly pick this. They think, well, it doesn't fall off, therefore outward and inward force have to balance. That would be true if it was linear motion or if it was not moving, okay? Here you have rotational motion. With rotational motion, you do not need the force arrows to balance. With rotational motion, you only have a force going toward the center, right? Because there is acceleration. If the force is balanced, that means there's no acceleration. That means net force is 0. And if the net force was 0, it wouldn't be moving in a circle, okay? This is also wrong. In fact, if you remember what I discussed in the previous video about centrifugal force, the made-up imaginary force used to explain why we feel what we feel when we're, let's say, moving in a circular path, this would be the direction of the centrifugal force. But the correct answer in the direction of the centripetal force is D. Okay, it's the center-seeking force. Please don't make that mistake as well. Okay, so that concludes 6.1, day 2 of 3. Stay tuned. Instructions and or maybe a video will be posted for 6.1, day 3 of 3.